All right. So now we have that solution. I'm going to move this over here to give myself a little more room. Now I want to apply my initial conditions to find my constants. So I can just use that first equation with the first condition, x of 0 equals 1. That should tell me that 1 is equal to c1 e to the 0, which is 1, plus c2 times e to the 0, which is 1. But now I got to apply my second condition. That's applied to the derivative here, x prime. So I have x, I can calculate x prime to be negative 2c1 e to the negative 2t minus c2 e to the negative t. I can then apply my condition to that, x prime of 0 equals 2, to get 2 equals negative 2c1 minus c2. I have two equations, two unknowns here. Lots of ways I can solve this system that I have here. I could write a matrix equation, do some linear algebra. I could solve one of the equations for one parameter and plug it into the other. In this case, as I look at it, I'm just going to add the two equations together. When I add the two equations together, I get 3 equals negative c1 plus 0. That tells me c1 is equal to negative 3. Plug that into my other equation. 1 equals negative 3 plus c2. Looks like c2 is equal to 4. And lastly, I form my final solution. Negative 3 e to the negative 2t plus 4 e to the negative t. Any questions about that solution? Sorry, where are we at? This line? Okay. Other questions, other comments? Okay, so, yep, question? It's a good question. So the follow up on that, I guess, is that what would it be then? Because if we're having two, so x of 0 tells us the value of x at time equals 0. So to have a second condition not involving the derivative, it couldn't be x of 0, right? Because x of 0 couldn't be at 1 and then also at 5 over here, right? Otherwise, I don't have a well-defined solution there. Okay, so that would be a problem. Now, if I can use my uniqueness in existence, that tells me that there does exist a unique solution, and all my coefficients are nicely for an initial value problem. Initial value problem means that all the information I have is about time equals 0. That's why I have to go x of 0 and then x prime of 0 at the second condition. Now, for those other groups of problems that don't deal with that derivative, that look like x of 0 equals 1 and x of 1 equals 4, for instance, so I'm given information about position but at different times. And those are harder to guarantee that there exists a unique solution. I could have multiple solutions that start here and travel to here. They go like this, could be a whole bunch of them. Whereas if I have a position that starts here and is traveling in that same direction, that usually fixes my solution. So the existence uniqueness is not as straightforward for those kind of problems. Yeah? Good question. Other questions? Okay, the last comment I'll make about this problem is this is solving the homogeneous equation. What we've seen since is that for the inhomogeneous equations, your first step to solve those is to solve the homogeneous equation. So this becomes one small step of that bigger problem. There are two problems that students usually have when doing this step. One is, okay, I either mess up my roots or I don't match the correct form, or I don't have it memorized well, so I get the incorrect form. But the other problem is time. These problems should not take a lot of time. You need to get enough reps on these problems where you are writing out that auxiliary equation, finding the roots, forming the solution. Okay? And so the faster you can be at that process, the more time you'll have for more complicated problems. All right, plan for today. A quick question here. So we had that quiz on Tuesday, kind of an in-class group resources quiz as part of a review. I just want to get a sense for if that was valuable or not. Right, so I found the group quiz as a form of review to be very positive, positive, neutral, negative. How about very negative? Right? Was there value in that learning process? Or would you rather have more of a traditional review where I work more examples. All right, good to know. And then next, would you like to see more of that in class as part of the lectures? I'm going to chunk out more lecture time to do similar kinds of group quizzes. Okay. Good to know. All right. One more quiz I'll add here. This is a really important one, okay? A, B, C, D, or E, grade that guy. What do you think? Start my little clicker here. No? Ooh, ouch. All right. All right. Well, we'll see how it goes. I'm from Wisconsin, okay? So, you know. All right. Okay. What are we talking about today? We're talking about inhomogeneous differential equations. We got a lot of questions about that last two problems from the homework and various parameters. So we're going to start off class by reviewing that process, going through it. I'm going to make sure that I give you a process for checking your work along the way. Okay? And then lastly, at the end here, we're going to introduce a new technique for solving these inhomogeneous differential equations. To start with what we have seen before, we'll start with a little bit of notation. So, given this operator, I'm defining my operator L, that is d squared plus 3 plus 2. That d is just that differential operator. It means take the derivative of whatever is in front of it. I'd like to find the general solution to L of x equals f of t. That's just kind of a linear algebra way, a linear operator way to write out my differential equation. Okay? I want to be very specific, so I'm going to actually give you an f of t. F of t is equal to 2e to the t. I'm basically saying solve this differential equation. And I want you to look at the differential equation and say, okay, left-hand side, that is L of x. That's what happens when I take that operator and apply it to x. I get that differential equation, right? So I'm basically reviewing that linear algebra notation to write that differential equation. Now I want to solve this thing. And I'm happy that it has constant coefficients and it's linear, but it is inhomogeneous. So what do I have to do? I got my steps here. That first step is to find the associated, the solution to the associated homogeneous problem. And we said we're going to call that our complementary solution. The solution to the associated homogeneous problem. All right, that's what I have this here. It's the solution to all that stuff equals 0. And we actually already did that, right? That was the warm-up problem. So we know that that one is actually going to be c1e to the negative 2t, c2e to the negative t, because we did that in the warm-up. And if we jump to that last step, the whole idea is our general solution, this differential equation, that complementary solution plus this extra piece. Now we start finding what is the extra piece. Okay? So there's a couple different ways we can find xp. One is variation of parameters. That's what we're reviewing today. And I really want to make sure that you understand the big picture, right? The process we're doing here, because that's really the most important thing. I know that when you leave here and you're going on to be engineers or whatever, you're probably not going to hand calculate W1 ever again, right? Or do a hand integral to find K1 or K1 prime and do those things. The most important thing I want to stress here is how we form this XP. We start by assuming that xp is equal to some function of t times one of our solutions plus some other function of t times our other solution of the complement or the homogeneous problem. We assume a form of our solution and then we plug it in to find the missing parameters. In this case, it's K1 and K2. That really is the whole process of variation of parameters. That's really all there is to it. The only problem is that solving for K1 and K2 is a little bit ugly. You have to make an assumption, do a little linear algebra. So that process is a little uglier, which is why we try to give you the mnemonics for W1 and W2 to help you memorize that, some of those shortcuts. But this is the core idea here. You make that assumption, you plug it in to figure out what K1 and K2 are. Okay? All right. Go back to some of the details here. So the idea is we did this. We made the assumptions. We plugged it in our differential equation. We did some stuff. We did some organization. And we got to one point where we had this guy and this guy equals the right-hand side. We said, well, if this thing was 0, that would be great. I'd just be left with this thing equals f of t. We basically ended up with a system that looked like this. It looked like x1 k1 prime plus x2 k2 prime equals 0. That was the assumption we needed to make. And then we had x1 prime k1 prime, x2 prime k2 prime is equal to whatever that right-hand side was. But when we plugged it in, we essentially got to this point, which we recognized is really a matrix equation. x1, x2, x1 prime, x2 prime times k1 prime, k2 prime equals this guy. So really all we needed to do to solve for K1 and K2 is to solve this linear system. And we can create an augmented matrix and do a whole bunch of things. But to generate a nice formula for our solution, one way we can solve the linear system is to use Cramer's rule. So at this point we used Cramer's rule to generate a formula for the individual solutions. This is all just under that umbrella of solving for K1 and K2 using linear algebra. And we found out that to apply Cramer's rule here, we would end up with the solution here, this first component of the solution should look like a determinant of this matrix, except we replace that first column with 0 and f of t. We leave the second column the same, divided by the determinant of that matrix. And the idea was that if you're strong on linear algebra, you don't have to memorize all this stuff because you've done it. So really it comes down to making your assumptions. But at the same time, instead of going that long process every time, if we know it's always going to end up in this form, it'd be nice just to jump to this step. And then when we look at that denominator, that matrix looks like that Wronskian guy we've seen before. So it makes sense to call that, the Wronskian. And then the W1 is just like a name trick, right? What's that thing in the numerator? It looks just like W, except the first column is different. Right? So you call it W1 for the little reminder how to form that guy. And then, of course, we do the same thing for the other one. A little mnemonic there. And you're going to need to know those values and how to calculate them. I just don't want you to get too lost in the mechanics so that at the end of the course you're like, how do you solve this differential equation? I don't know, it's a W1 and a W2, right? I want you to see the big picture of making that assumption, plugging it in, and finding your solution. All right, I'm going to do one side of this so we can see the process. I won't do all the computations here, and then we'll let you have one to play with. And then I'll show you how I'm checking my work along the way. W1 is going to be 0 and 2e to the t in this case. And then x2 was e to the negative t, and then negative e to the negative t when I took the derivative. The Wronskian is going to be e to the negative 2t, negative 2e to the negative 2t. This column stays the same. And I just calculate these values. So in the numerator, I take that product, which is 0, minus this product, which is 2 times Well, e to the t times e to the negative t is what? 1. So I just got 2 in the numerator. Negative 2. In the denominator, I get this product. So that's negative e to the negative 3t minus this product, which is negative 2e to the negative 3t. Negative 2 in the numerator, positive e to the negative 3 here. Maybe I'll just write like that, like negative 2e to the 3t. Just calculating k1 prime. Of course, what I really want is k1, so that means I have to integrate k1 prime. And I do that to get negative 2/3 e to the 3t. Questions so far? Make sure if you have questions about some of those exponents or how those values got in there, make sure you ask. Oh no. All right. Any questions? Yep. Sorry, say that again. That should be 2e to the t. All right, so I have k1. I can do the same thing over on the other side. I'm just going to tell you what the answer was. k2 ended up to be e to the 2t. And the idea is, what do we do with these guys? Now we have to form our solution. So xp is supposed to be k1 x1 plus k2 x2. So I got negative 2/3 e to the 3t. That's k1 times x1, which was e to the negative 2t, plus k2 e to the 2t times x2, which is e to the negative t in this case. And that's my particular solution, xp. Now, a couple things I want to point out here. You have to do an integral along the way. If you work on that homework, you got stuck on that number 5 problem. So what do? What do you expect to know here? Now, quizzes or exams, I'm not going to have nasty integrals. We have to figure out what nasty means. I expect you to do basic substitution problems, basic integration by parts problem. No partial fractions, no trig substitution. That's easy. I want you to try to get through the integrals. If you can't do the integral, then leave it in the integral form and just write out your solution with an integral in there. At least then I can give you points for forming your complete solution. If you can't do the integral and you just stop, I can't give you any more credit. But if I can't do this integral, and I write xp, is equal to, well, let's see, x1 was e to the negative 2t, and k1 was the integral of negative 2 e to the 3t dt, plus that other stuff. You know, you might lose a point if it's an integral you should know how to do. I'm not going to kill you. You'll get a lot of less credit. Any questions about that? You know, a reminder, all phones should be away and put away, not on desks. Make sure they're all off of the desks. Thank you. All right. Any questions about that? Okay, I do want you to do the integrals, though, because if you actually do the integrals, a lot of times you get simplifications like this. If I simplify this, I get negative 2/3. That simplifies to e to the t. Plus this simplifies to e to the t. This simplifies to 1/3 e to the t. That's much easier to use in that big, long, ugly expression. So you want to do those simplifications when you can. And then finally, you need to be able to form your final solution, c1 e to the negative 2t, c2 e to the negative t, plus 1/3 e to the t. That is the final piece here. Okay? Yep. Specific solution? Sure. So if I had initial conditions, now is when you'd go by to find those constants. You can't use your conditions to find your constants from just your homogeneous solution. You got to make sure you get xp in there, okay? Once xp is found out and you have this form, now you can use initial conditions to go find those constants. Okay? Other questions? All right. This was that nasty one from the homework. If you haven't done it, please start it now. If you have done it, work through what you can get here. I'm going to give you a head start, and then I'm not going to work through it, but I'm going to show all the calculations along the way in Mathematica in a way that you should also kind of keep track of your work. That way you can find out exactly when you make a mistake, instead of doing a whole bunch of work to get to the end and having to go back through all your steps. I'm going to show you kind of a little systematic way Mathematica check the work along the way. Go ahead and get started. Find that complementary solution. Auxiliary equation. And now you should probably have your complementary solution. Give me W2 over W. Thank you. Okay, so I want to get started here, do a couple steps. Now, the first thing I need to do is find that complementary solution. And so I'm going to do that by hand. I'm going to generate my auxiliary equation. I'm going to go find those roots. I'm going to get them and be happy with that. But what I can do when I'm done is I can check real quick. I can just desolve the associated homogeneous problem. X double prime of t minus 2 x of t, x prime of t, plus x of t equals 0, x of t comma t. Okay, so now I can kind of verify to see if I've done that first step correctly. Do I have e to the t and t e to the t? Do I have those two as my solution to the complementary solution? Okay. Anybody have any questions about that step? Do we get there? Okay, so we have repeated root. So I had to modify that second solution. All right, so the next thing I have to do is calculate, my W1, my W2. And to do that, I have to figure out x1, x2, x1 prime, x2 prime. I'm just going to do all that stuff right here. I'm going to do x1 of t. That guy is supposed to be, how about e to the t? There we go. I'm finding that guy. x2 of t. That guy is going to be t e to the t. And so now, after I do my calculations, I can verify if my derivatives are correct. If I type it correctly, that is. There we go. That one we shouldn't have too much trouble with. This one, however, you can go too fast and make a mistake here. So now I can just quickly verify if my derivatives are correct. But what I really want to do is form all those W guys. So what I can do here is I can say, let W equal, I'm going to create a matrix in here. So I have a parentheses. My first value is going to be x1 of t. I'm going to hit control, comma. Control, comma, lets me start a new column. This should be x2 of t. Control, enter, allows me to start a new row. What's going to be down here? x1 prime of t. What's over here? x2 prime of t. And now I have W. And what do I really want? Well, really what I want is the determinant of W. Here's my determinant of W. Is that what we got for our Wronskian value? Can we confirm that Wronskian value? All right, I'm going to leave that one up there. I'm going to give it some more time here and keep calculating. So you get W1, W2, form the ratios. All right, I'm going to do some more calculations here. I want to get the other one, so all I'm going to do is I'm going to go control, copy, paste, paste. Okay. And then what is W1? Well, it just says get rid of that first value. And down here should be whatever my right-hand side is. Oh, I haven't defined that yet. So maybe I'll go back up here. I'll define f of t to be e raised to the 2t over 1 plus e to the t quantity squared. Okay, so now I define my function there. So now I have W1. W2 is just going to be, here's W2. That's just going to be a 0 over here. And f of t here. Okay. So now I can run those values and store all those. I can look at them if I want to check things out, or I can hide them. Because really I don't care about those things. Really what I care about is the determinants. W, W1, and W2. And so now I can see those values. So, how are we doing on those values? All right. So you have those up there. See if you can figure out, confirm those, check the mistakes. All right, what's K1 prime? Well, K1 prime should just be the determinant of W1 divided by the determinant of W. All right, that should be K1 prime. There's my value for K1 prime. What's my value for K2 prime? K2 prime should be just W2. And the idea is to find K, we have to integrate these things, right? And that can be easy or hard depending on the problem. Once again, I expect you to be able to go through some basic techniques. So for this one, I consider that basic substitution. We let u equal 1 plus e to the t. Everything should work out. You're going to end up with something like, it looks like 1 over u squared. Integrate that and you should be good, okay? This one, however, is harder. So if it's me working that guy out, I'm going to look at it. Maybe I try a substitution like u equal 1 plus e to the t. I could actually do that. I'll put on an extra factor of t in the top. I can take my substitution and solve for t. I get some weird stuff in the natural log. When I would write that, I would probably recognize that I got something like a u times the log of u. That might rely on the integration by parts on that. But once you get past that second step, it's a harder interval. Right? So good practice. I encourage you to do it. You will balance your own time. If it's one of those hard intervals, use mathematics. It's your calculator. You don't need to. Okay? So for me, I'm doing the first one with Mathematica. The second one I can see what I'm going to do, so I'm going to do that one by hand. If you're not sure, do it in Mathematica. You'll see the result again. If the result is a hyperbolic sign of natural log of something crazy, that's probably a hard one. If it ends up to be like e to the 2t, well, maybe there's a substitution you can look for there. All right. So I have these values. Then I'm just going to integrate. How about K1 prime with respect to t? It's going to give me a bunch of ugly stuff because that one was hard. I'll do the other one. It's right here. That one was easier. Okay. I can verify my values for K1 and K2. Now if I want, I can put them in my full solution. Try my final answer with DSOLVE. Okay. And when you're done with this notebook, you just scroll back up and I can just change X1, X2, and FT and rerun and see all the steps along the way. Okay. So 2 comments about that. One, I'm going to preemptively answer the question of can I send you this notebook? No. Right. You guys can create this, all right? It's good practice to go through here and find some of these things. Really, the only things you should do, you've probably not seen yet, maybe are the matrix stuff, control comma, control intermediate matrices, maybe that determinant command, DET. So I would encourage you to do this along the way, because it really does help. Of course, this is to support the process, right? You should be doing your hand calculations first, and then verify them. But check them right after your steps, right? Don't spend 3 hours going through a big long problem, put it on the website, get it wrong, and find out that in your very first step you dropped the negative sign, right? Do a couple steps, check your steps along the way. Do a couple more steps, check your steps. Okay? Any questions? All right. All right, so that really wraps up variation of parameters. The rest is just repetition. You really just got to get in there and do problems. But there is another technique we have for solving these inhomogeneous differential equations. This next technique is what we call undetermined coefficients. Now, the nice thing about variation of parameters is that it pretty much works with any problem you're going to run into. Any inhomogeneous differential equation, you can use variation of parameters to find that ST piece. Not so for some coefficients. Okay. One restriction is that it will only work if we have constant coefficients. And that's not a huge deal to us because honestly, if there's not constant coefficients, we can't find the complementary solution anyway. So that's not super restrictive to us. The other big restriction on what that right-hand side can be. If this is equal to f of t on the right, for undetermined coefficients, that stuff on the right has to be something we would get from one of the solutions to the complementary piece. In other words, when we find complementary solutions, what do we get? We get polynomials sometimes, we get exponentials sometimes, and we get sines and cosines sometimes. Those are the only functions we get from solving those homogeneous equations. And so f of t, the stuff on the right, has to be something like that. It can be polynomials, exponentials, sines or cosines, or any sum or product of those things. Okay? So that's a 1 over t on the right hand side. I can't use this technique. I have to use variation of parameters. Any questions there? All right, how do we use this technique? Undetermined coefficients. Same step 1, find the complementary solution. Right, that's the same. In this case, we got r squared plus 2r minus 8 equals 0. It looks like that factors into r plus 4, r minus 2. That means we got r is equal to negative 4 and 2. So it looks like my complementary solution is c1 e to the negative 4t, c2 e to the 2t. Okay? All right. Now the important stuff, the assumption, right? We've seen there's 2 ways to solve differential equations. We monkey with it until we can integrate it, or we make some inspired guess. Our inspired guess here is that I'm going to assume the xp looks like the right-hand side. The right-hand side here is a first-degree polynomial. I'm going to assume xp is a first-degree polynomial. That is my assumption. Okay. That is my assumption. Now I have one more in between step here, which is checking for the overlap of the complementary solution. The idea is this. I guess that my particular solution is ax plus b. That first piece is, I'm sorry, it should be t. Run back over here. AT plus B. Right hand side is the function. There we go. I'm guessing that particular solution is AT plus B. So the first part is like some number times T. If some number times T is one of my complementary solutions pieces, that's a problem. So when I plug in that piece, I'm basically going to generate a zero value. So that can't happen. Now my other part was just a constant, B. If one part of my complementary solution is a constant, it's a problem. I have to adjust for that problem later. Okay? We'll talk about how to adjust for that on the next time. Okay? I have to check to see if there's an overlap there. Okay? In this case, no overlap. Right, my complementary solution is a bunch of exponentials. They look nothing like AT plus B. I'm all set. Okay? So my guess is XP is AT plus B. All I need is to figure out what A and B are. How am I going to figure out what A and B are? How do I find out what K1 and K2 were? How do I figure out what R was for my complementary solution? Complementary solution. I assume my solution was going to e to the RT. How do I find the right values of R? Took the derivatives, plugged it into the differential equation. How do I find K1 and K2? Took the derivatives, plugged them into the differential equation. Same thing here. Go ahead and take the derivative of XP. Take the second derivative of XP. Plug it into the differential equation. Go ahead and do that for real. Let's see if you can solve for A and B. Everybody see where that equation came from? You see those derivative calculations? The derivative is just A. The derivative is like T here. That derivative is 0. I just plug them in. X double prime. Well, that's 0. 0. Plus 2 times X prime. Well, if X prime is A, 2 times A. Okay? That's it. Now, how do we solve for A and B? The best way to solve for A and B here is to reorganize the left-hand side to look like a polynomial. I got a polynomial on the right. Let's make it look like the polynomial on the left. On the left, there's a polynomial. See, there's a t term. So I'm going to group all the t terms together. I get negative 8a times t. I'm going to take all the constant terms. There's a constant term. There's a constant term. I'm going to group those together. It looks like I got 2a minus 8b. And that's supposed to be equal to 8t plus 6. I have a polynomial on the left. I have a polynomial on the right. Two polynomials are equal if and only if their coefficients are equal. That's a fancy sentence, right? What that fancy sentence means is this. AT squared plus BT plus C, if that's equal to 2t squared plus 3t minus 4, what is A? What is B? And what is C? Negative 4, right? That's it. That's all I'm doing here. All I'm saying is that here's the coefficient to t, negative 8a. That has to be the same as the coefficient to t on the other side. Okay? What's left? I got a bunch of constants, 2a minus 8b. If that's equal to this other polynomial, it has to be equal to this constant. Okay? And then I just solve for my values. Looks like a is equal to negative 1. I plug that in over here. Looks like b is also equal to negative 1. So I guessed my particular solution was AT plus B. Turns out the right A and B to make that true are -1 and -1. So then lastly, my final total solution is some constant e to the -4t, some constant e to the 2t, minus t minus 1. So once on the left, I figured out what A was. I figured out A was -1. You're really just looking for it. So my YT last time had e to the 4t. So when I form my guess, and my guess says some number times -4t, that's the overlap. If I have the same pieces of my guess that I do in my number. We'll look at some specific cases next time. Other questions? Yep. So second question, let me just put the exact case here. Let me zip here real quick. Here we go. Here's the case of this. The idea is this. If I want to find my complementary solution here, I would form my auxiliary equation like this. I would solve for my r values. In this case, it would be r plus 1 squared equals 0. So my complementary solution would be C1 e to the -t plus C2 t e to the -t. That's my complementary solution, right? We'll leave that guy there. Now I got to find a guess for my solution. Well, if my right-hand side is some number times e to the -t, it makes sense for me to guess that my solution should look like some number e to the -t. That's what I would guess. But now I look at my complementary solution and I say, uh-oh, some number e to the -t, some number e to the -t. Crap. That's what I mean by overlap, right? If I plug in this xp to try to find a, it's going to give me 0 because this is a piece from the complementary solution. Okay? So the adjustment I have to make, I say, uh-oh, bad guess. New guess. Multiply that thing by t. When you have a bad guess, multiply it by t. We can do reduction of order to show why this might work, but it's a long process. Multiply it by t. But then check again. Is this thing my complementary solution? It is. Okay. Guess again. AT squared e to the -t. Is that thing in my complementary solution? No. That means this will be my official guess. Now I'll take the overtime, you won't be able to what? No. There are other cases where you can't. For this method to work, that right-hand side has to be one of those special functions. It can't be logs, it can't be tangents, it has to be polynomials, exponentials, sines or cosines, or the product and sum of those things. That's what I'm going to now, there are other problems we're going to run into as well about our guess. We're going to have to be a little creative with some of our guess. So we're going to start class with that next time.